When I was teaching in Montana, I would always point to that picture and ask them where that choir was, where that organ was, and there was always someone from the YSA ward that would raise their hand, but most of the people had no idea. But I'm pretty sure that everyone in this room knows where that is, Temple Square. Today we're going to talk about longitudinal standing waves. And the good news, the great news, is that they act very, very much the same as the transverse standing waves that we talked about last day. Only in this case, we're talking about standing waves in air, sound waves that are passing through each other and setting up these standing waves. I almost blew myself up with this demo here at the beginning of class, so maybe we should have a prayer. Would someone pray for safety today? Anyone got a good safety prayer? Thank you, sir.
Dear Father in heaven, just love you all from the class today. We pray that we'll be attentive and be able to learn all we need to before our next exam. Help everybody be safe in the demo, and it's in Jesus Christ.
Amen. Thank you. Okay. So what we learned last day was that when the ends were the same, when they were both nodes, a node at the left, node at the right, you started with a wave length that was twice the length of the system. Remember, it takes how many footballs to make a wavelength? Two, always two. And what we've got in that top picture is just one football. And so we have half a wavelength in there. I say we've got one football. And that's the first harmonic or the fundamental. Every time we go to the next allowed resonance, the next mode that will resonate, we have to add one football. So we go from one football to two footballs to three footballs to four footballs. Now, if I go from one football to four footballs, I've crammed four times as many footballs into the same space. That means my footballs are 4 times smaller, right? And by my wave equation, which Sam helpfully erased for me there, if the wavelength gets 4 times smaller, the frequency has to get 4 times bigger. And that's why if this were 100 hertz, this would be 200 hertz, 300 hertz, 400 hertz, and so forth, okay? Now, we also found, here we go. That's the wave equation right up there. And since the wavelength is getting smaller by a factor of 2, 3, 4, the frequency has to get bigger by that factor because the wave speed stays the same. Okay. Sam, why don't you write up a formula over there for the wave speed in a transverse wave, the square root of the tension over the mass density. We found last day that there was another flavor. We found that in cases where we had ends that were different, where one end was a node and the other end was an antinode, that we didn't start with one whole football. In that case, we started with just half a football. But the old rule still applies. Every time I go to the next allowed resonance, I got to add one whole football. So this one I would call the first harmonic or the fundamental. But the next allowed resonance, I still have a node at the post. I still have an antinode there. But now I have to add one whole football. Now, since I started with half a football, adding one football doesn't double the number of footballs, it triples the number of footballs. I have 3 times as many footballs in the same space. My footballs are 1/3 as big. My frequency is now 3 times as big. And so what I find is that I go straight to the third harmonic. The second harmonic does not exist in this system where one end is a node and one end is an antinode. And that's just a general rule that's going to also apply today with longitudinal standing waves in organ pipes, okay? We find that if the ends are the same, we get all the harmonics. If the ends are different, I only get the odd ones, F1, F3, F5, F7, F9, and so forth. Check that your neighbor understood that from Tuesday's lecture, please.
That's the right selection, but you know, I
Okay.
and he's basically saying like everybody's go to his then it's gonna go up.
Now,
I
I'm guessing that everyone in the room has set up a longitudinal standing wave at some point in their life. You do it this way. Now, as I blow across the top of that, I'm just creating what we call white noise, a sputter, all sorts of frequencies. And there's one frequency that wants to resonate. And by resonate, I mean it wants to boom, okay? And that's the fundamental frequency, okay? That's the one that just nature picks out of the white noise and amplifies. Now, I could also excite other harmonics in here. Now, what we find is that if I have a closed end at one end, well, that's going to be a node. My molecules can't go anywhere. They can't vibrate against that solid surface. But the open is going to be an antinode. Okay, and so what I have here is a system where I would have F1, F3, F5, F7. F1 is the one that nature's going to pick if I just give it all the frequencies, but I could also excite it at its third harmonic if I used a tuning fork, and I'll show you that in a little bit. Okay. Now, here I need to apologize to you. When we were talking about transverse standing waves, we use this notation here and the football notation. And you see that what we had was a string that was in the shape of those red arrows. This one here was up, and this one was down, and this one was up, and this was down. And then a half period later, it was the blue arrow. And you would see that these things would go like that, okay? And transverse means perpendicular. These waves, the two traveling waves that make the standing wave, are traveling left and right. But the displacement is perpendicular to that, up and down. Now, a longitudinal standing wave is a sloshing, kind of like the slinky. And there, what we see is that the football representation is really, really poor. And yet we still use it. It's just common in all textbooks to use this representation of a longitudinal standing wave. But all it tells us is where the antinodes are and where the nodes are. Nothing else. Because nothing's going up or down here, it's going left and right. And so what's happening is all the particles, like in air, in a column of air like a organ pipe, all the particles would be moving first with the blue arrow, okay? And you see that all of the particles in this football are moving to the right. All the particles in this football are moving to the left. And the closer you are to the antinode, the bigger the displacement away from equilibrium. And the closer you are to a node, the smaller the displacement from equilibrium. Okay, so Let me see if I can help you visualize that with this demo. This demo, we had one of these devices in Montana, but they don't sell them anymore. And I didn't think to bring it with me. It didn't belong to me anyway. But we have a video of it being used.
This device is used to demonstrate longitudinal waves, where the displacement of the medium is parallel to the motion of the wave. When the first rod is pushed sharply, springs between the rods pass the motion along. If the first rod is moved back and forth at certain frequencies, standing waves appear.
Now, at the top of each of those magic wands is a yellow dot that represents a molecule of air, okay? And that series of dots are moving, they're sloshing in such a way that the nodes are being crunched and the antinodes are being deserted. I do this demo so much better than she did. I'm sorry. So we'll represent it with a little bit of an animation here. When I put those blue dots there to represent the location of my node. And you see that when this node is being crunched, the C stands for crunched, it's being attacked from both sides. Its neighbor is being deserted, and its neighbor is being crunched, and its neighbor is being deserted. And then this sloshing happens back and forth, and so the node that was being crunched goes to being deserted, and then it goes to being crunched, and then it goes to being deserted, and we just slosh back and forth, okay? Now, the football representation, again, only tells me where the nodes are and where the antinodes are, where the motion is the most and where the motion is nothing, okay? But the molecules are just essentially, they're just going back and forth, back and forth, back and forth, back and forth, back and forth. And you see, if you look at one of these nodes, it goes from being deserted to crunch, deserted to crunch, deserted to crunch. Now, if you're not seeing that, if that's just not speaking to your soul, I suggest tonight you go to your bathroom if you've got a tub, fill up the tub, lock the door, okay? Lock the door, because you're going to get in that tub naked and you're going to scoot your bum, okay? And you find just the right frequency so that you get the sloshing going to where you got a wave in the middle, okay? That's F1. Now you scoot your bum twice that fast, and you're going to get another node in there. That's F2. And eventually, you're going to have to clean up the water on the floor, okay? Because it's going to get out of hand. Okay. You didn't learn that from me. I have here just you know what? Let's do this first, okay? What I have here is a tube filled with propane, and if I send frequency through these two speakers, I can set up a standing wave in that tube. And you can see that that's the third harmonic, okay? Oh, sorry. Now, if I change the frequency of one of those speakers, I have one of them set at 320 now and one set at 319. What's going to happen? Tell your neighbor. We get a beat frequency of 1 hertz. And if I change the other one to 318, I get a beat frequency of 2 hertz, then 3 hertz, 4 hertz. Okay. Now, let's go back to where we were. And that is this aluminum rod. This is just an ordinary aluminum rod. It happens to be 7 feet tall. Yes, it is. And if I squeeze it in the center,
Is he doing that? What the heck?
I can make it sing. Now, I can make it sing louder if I use a leather glove and put some rosin on my glove and on the rod here, just to make it a little sticky. And what I'm doing as I rub this is I'm creating the white noise, all the different frequencies. And so let me get that started again.
Oh, that's good.
Yeah. Now, that is a longitudinal standing wave. I can also set up a transverse standing wave that'll sound very, very different. In this case, if I had special glasses that could see microscopically, what I would see is the molecules in the lattice work vibrating a lot at the end. That's an antinode. Not so much here, a little bit. And where I'm squeezing it, not at all. That's a node. And then a little bit and another antinode there. Okay? And that's what you're seeing as a standing wave, but really it's 2 traveling waves, one going up the rod and one going down the rod, passing through each other, as we learned last day. Now, my question is, if Greg squeezes there a quarter from the top instead of in the middle, what's going to happen to the frequency? Will the frequency go higher, lower, or stay the same? Let me get you started. Okay, now you can click.
I think I'm totally farther away from.
I know, I'm like, obviously violin. Well, because for me, I was like, the distance it has to travel, right?
Okay, get your attendance points. If you haven't clicked yet, be sure to click.
I've never read it.
Almost like if he goes higher, it's slower.
Okay, what we said was that the frequency will get lower. Okay, so let's find out. I'm going to go back to the middle again. memorize that note.
That in.
Okay, this is quarter of the way. Here's the mark. Okay. Where was that?
Who's a witch?
There we go.
Ow.
Again, it was so funny that this.
It went higher. Went higher. Most of you got that wrong. And I would ask those of you that says it's going to get lower, what were you thinking? And I'll tell you what you were thinking. You saw that this part of the rod got longer, and you knew that the long organ pipes made the low notes at the tabernacle, okay? What you failed to notice was that this part got shorter, and this end has to stay an antinode, and where I'm squeezing it has to stay a node. And so my distance between node and antinode was just cut in half. Visually, what that looks like is that I started with this wave here, where there was a node in the middle, and the vibrations were the greatest at the end. And we call that the first harmonic. And essentially, I've got one football there, right? I've got a half football on the left, a half football on the right. Now, this is the first example we've seen where we're going from antinode to antinode. But we're still going from the same. Same on the left as what I've got on the right. So if the ends are the same, I get all of the harmonics. So the next harmonic would be the second harmonic, and it would look like that. And it would have two footballs, a half on the left, half on the right, and one in the middle. And so that means my frequency is going to be double what it was before I have the second harmonic. Now, this makes a very, very interesting prediction. There's going to be one node right there where I'm squeezing, but if physics is true, I've got another node right over here, a quarter from the other end. Well, let's test that out. Let's see if we can validate that. I'm going to get a little bit more of this sticky powder. Okay, get that on there. Now, this really requires me to know where the quarter mark is, and it's not marked on this end. So let's see. Halfway. Let's call it there. Oh my goodness. Okay, so there's the center. I want halfway in between there. Is that it?
Higher.
Higher? Go higher?
About there, yeah.
Okay. You got it. Now, if I grab this here, it keeps singing because that was a note. It wasn't vibrating there anyway. But if I grab it anywhere else, it stops. Okay? See if your neighbor understood what happened there.
Myself.
That's sick or what? That's just a all morning. Physics? Bro, insane.
Well, antidote for.
Okay, let's try something else. If that's a quarter, that's a quarter. That's an eighth. I hope you can hear that. I can't. And if we go here. Now only the dogs in the neighborhood are gonna hear that. Okay. Okay. I love my job. We get to play, call it work. Okay, let's talk about organ pipes. Organ pipes come in two flavors, open and closed. And when we say an open organ pipe, what we mean is open at both ends. Now, this organ pipe is clearly open at this end, okay? But it's also open at the other end through this little slit where we are essentially creating white noise. The air going past this slit is creating all the frequencies. There's one frequency that's going to resonate, boom, with this organ pipe, and it's this frequency here. Okay. Now, what wavelength do we have there? Well, the open ends of an organ pipe have to be antinodes. Okay, and so I'm going from an antinode on the left to an antinode on the right. And you can't go straight there. That's just wind. There has to be a node in between so that I get the sloshing going on where the nodes are being crunched and deserted and crunched and deserted and crunched and deserted. That's what makes the vibration that travels across the room and assaults your eardrum that you call music. Okay? Now, since I only have one football and it takes two footballs to make a wavelength, I've only got half a wavelength in there. So that means the wavelength must be twice the length of that organ pipe. And that we call F1. And that's that combination of variables that we called a Charlie last week. Now, a closed organ pipe, what we mean by that is closed at one end, okay? If you close it at both ends, that's a box, and you don't get any music out of that. A closed organ pipe, what we mean is closed at one end, open at the other. Now, the closed end has to be a node. The molecules can't vibrate there. There's a hard wall there. But the open end, again, is an antinode. And whenever we have different ends, one a node and one an antinode, we can only fit half a football in there. And that's only a fourth of a wavelength. So that means the wavelength now is 4 times the length of the pipe. And we get that for the fundamental frequency. Now think about designing an organ for the tabernacle. When the saints came across the plains and they built that wonderful, wonderful tabernacle, the ceiling's only so high, okay? And if you want to get some organ pipes that are really, really low, remember, low notes are very, very long wavelengths. And if the wavelength is too big, so it won't fit in your tabernacle, what you do is you use closed pipes, because you only have to fit a quarter of the wavelength into them. In order for an open organ pipe to play the same note, it would have to be twice as long. Twice as long. Let me see if I can demonstrate that. This is open at both ends. That's the note that it makes. I'm going to close one end. Let me see if I can do that without kinking. Let's try it over here. Here, instead of my hand, I can use that. Sam, come help me. I'll just blow in and you pump it up. Ah, there we go. Thank you, Sam. Let's do it again. Okay. Thank you, Sam. Oh, there's the organ pipe. Now, what about the next harmonics that will resonate?
These.
Well, in the case of the open pipe, I go from 1 football to 2 footballs. I double the number of footballs that fit in the same pipe. That means my footballs got half as big, which means my frequency doubles. And this is F2. It would be twice the original frequency. If instead I have a closed pipe, closed at one end, I started with half a football. I got to add 1 football every time I go to the next allowed resonance. And so this time I'm going to have 3 half footballs. Well, 1.5 is 3 halves. I've tripled the number of footballs that fit in the same pipe. That means my frequency has to get 3 times bigger. And so this is F3. I go straight from the first harmonic to the third harmonic, skipping the second harmonic. Indeed, I will also skip the 4th harmonic and the 6th harmonic and the 8th harmonic. Only the odd harmonics will resonate. And that's because every time I add a football, if I started with half, if I add a whole football, I'm skipping one of the resonances. I go from 1/2 to 3 halves to 5 halves to 7 halves footballs. See if your neighbor is following this. I don't want anyone left behind here. Are there questions?
Different.
Okay. Again, if the ends are the same, either both nodes, like a string that's tied at both ends, or the aluminum rod that's an antinode at both ends, I get all of the harmonics, 1, 2, 3, 4, 5, 6, 7, 8. If the ends are different, like the closed organ pipe or the hacksaw blade, I only get the odd harmonics. Again, a lot of the rules that govern standing waves work for both flavors, the transverse standing waves, the longitudinal standing waves. You just have to visualize them different, as the one case is a sloshing, whereas the other case is something going like this, perpendicular to the waves. Now, last week, last Thursday, when we were talking about beat frequencies, I showed you that I could make this booming sound with an aluminum tube over a flame. And the flame, again, you remember, was just making the white noise. And the frequency that was booming was the first harmonic of that tube. And that depended on the length of the tube. And I had an antinode at the top of the tube and an antinode at the bottom of the tube. I wasn't exciting it with a tuning fork. I was exciting it with the white noise of the flame. But I could have excited that with a tuning fork if I knew just what frequency of tuning fork to use. And then if I got twice that frequency tuning fork, I could also get a resonance, a booming sound with 2 footballs in it. Now, if I had a cylinder that was closed at one end, so that the molecules couldn't move there and it had to be a node, now the fundamental frequency would give me half a football, and 3 times that fundamental frequency would give me 3 half footballs. Now I have a demonstration of that. I have here a a tuning fork that is 341.3 hertz. Now, you remember that the speed of sound is about 343 meters per second, okay? So if I use this wave equation, and this is 343, and this is 341.3, this is about 1. And so the wavelength for this tuning fork is about 1 meter long. But I don't have to fit a whole wavelength in here. I've got water forming a fixed boundary at the bottom. That's going to be a node. And at the top, I've got an antinode. So how much of my wavelength do I have to fit in this column of air here? Tell your neighbor real quick. It's half a football node to an antinode. How much of a wavelength is that?
5 cents.
1/4. And so I need an air column that's about 25 centimeters long so that it would fit 1/4 of a wavelength. Now, I've set this up so that that air column is 25 centimeters long. Now, when it's over here, you can hear it, but in the back you can't. But when I get it over the column, now it's not just the tuning fork making sound, it's the air in this cylinder that is resonating with that. So, okay. Now, if I go twice that frequency, you don't get that resonance. The even harmonics don't exist. But if I go to 3 times that frequency, which is 1024, it resonates. Okay? Is that cool or what? Okay. Now, let's look at some quick problems here. Now, the lowest 4 frequencies at which an air column will support standing waves are measured to be 75, 25, 375, and 525 hertz. What is the length of that air column? Okay. Now, the first thing that we want to figure out is that an organ pipe that is open at both ends or closed at one end? Tell your neighbor, which is it?
First harmonic.
Okay. By show of hands, how many say open, open? Open, close. Oh, I love you people. That's wonderful. And the secret is right there. That's obviously F1. The question is that F2 or is that F3? Yeah, if it were F2, it'd be twice F1 or 150. But instead it's 3 times F1 or 225. And so that's F1, that's F3, that's F5, that's F7. And so that means I have a pipe that has some length L that I'm looking for. I also know that the fundamental frequency of 75 hertz is going to look like this with half a football. And so that means that the length of that pipe is going to be 1/4 of the fundamental wavelength. Does that make sense? So if I can find that fundamental wavelength, I'm home free. Well, I use this equation here. And if I use it for the first harmonic, I can find that fundamental wavelength. Now, folks, I wish I had a happier tale to tell, but I'm an old man and I've seen this over and over again. People during the exam get high centered, they get stuck because they don't know what velocity to put in there. It's an organ pipe. These are sound waves. What's the velocity? 343, 343. That's a given, okay? So 343 meters per second is equal to lambda 1 times 75 hertz. I can find lambda 1, and then I can divide it by 4, and that's going to give me my length. Check that your neighbor's on the bus there. Okay. Are there questions on that problem? Okay, let's look at another one. We have a cylindrical tube, and it's the same standing waves at a frequency of 500, 700, 900, but not at 600 and 800. And the question is, what is the fundamental frequency of that tube? And is it open at both ends or closed at one end? Again, if I write down the frequencies that resonate, and I look at how they're separated by 200 hertz. So if I march down by 200 hertz, and remember not to go negative or not go to 0, this has to be F1. It's the lowest frequency that resonates. This is 3 times that, so that's F3. This would be F5, and this would be F7. Because the even harmonics are missing, this is going to be a tube that is closed at one end and open at the other. And if I were to ask you to find the length of that tube, we would do exactly what we did in the last example. Check that your neighbor could do that on an exam, because again, I have a feeling, a really, really strong feeling, that you will have to. Okay?
Down.
Okay. That's also going to help you with the homework that's due next Tuesday. Sam, where did I? Oh, there it is, right there. Many, many years ago, when I was teaching with my friend Jeff Adams, we put this problem on the exam as problem number 1, because we thought it was the easiest problem on the exam and that everyone would get it right. The problem is you can tune the frequency of a guitar string without changing its length. To tune a flute, however, you have to slightly adjust the length of the tube. How do you account for this difference? What we found that night when we graded the exam was that almost nobody got it right. And the most common wrong answer was flutes don't have strings. If they had strings, we'd use them, but they don't have strings, so we got to do something else. It's really hard to argue with that logic. They don't. Okay, I know that much about music. This is what we were looking for. When we're looking at a guitar string, it obeys that wave equation. And in this case, that V is governed by the tension in the string. Now, what can change and what can't change? Well, it turns out that for the fundamental frequency, if I don't do any fingering of the frets there, my fundamental is going to have one football, and the length of that football is going to be from there to there. That doesn't change. And so that means if I want to tune this thing, and tuning means getting that frequency to either be higher or lower, I have to change the speed of waves on that wire. Now, the wave speed depends on the tension in the string. And so all I have to do to make that frequency higher is tighten the string. To make it lower, I just loosen the string. But for a flute, they don't got strings. So what are we going to do? Well, they still obey this wave equation, but now if we ask what's the same, what stays constant, in this case, it's going to be the speed. The speed is going to be 343 meters per second. Now, I feel stupid saying that because my son was on the marching band in Bozeman, Montana, and they would tune up their instruments in the gymnasium and then march out onto the field at 30 below zero. And suddenly nothing was in tune, okay? Because the velocity of sound changed dramatically once they got out on the field. But if you stay in the gymnasium, the speed of sound stays constant. So that means that in order to change the frequency, to tune it, I've got to change the wavelength. And to change the wavelength, I've got to change the length of the tube. Now the question is, what am I doing when I change that length of the tube? Am I changing it so that I can fit more footballs or that I can fit different footballs in there? Talk to your neighbor. Which is it? Do I want more footballs or different footballs? Okay. I hope you can see that we want to change the length of our footballs. This tube here has exactly the same size footballs as my original tube. These are playing the exact same note. If they have the same size football, they have the same wavelength, they have the same frequency. It's just that this tube is playing it at the first harmonic. This is playing it the same note, but at the second harmonic. I have to change the length of my footballs to change my wavelength and hence change my frequency. And I don't want to double the length of the footballs. I just want to change them by a little bit to tweak the frequency. Okay, and that's what you're doing when you're lengthening that flute. Talk to your neighbor, see if your neighbor knows how to play a flute.
It is, so.
We'll make it like a trend.
High quality.
Oh.
Yeah, it's been better.
It's like, and I was like, okay, no, that's fine. So then I had to.
Come back. Oh, let me answer that for everyone there. An important question was asked just now, and that is, why is the velocity changing for the the guitar string, but not for the flute. And that is, this equation always, 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 in every case, works for the velocity of the wave. Whether it's a standing wave, traveling wave, transverse wave, longitudinal wave, doesn't matter. But we have another set of equations. We have this one for transverse waves. Can spell like waves on a string, like a guitar string. And we have this formula that's a very simple formula for sound waves, like in a flute, longitudinal waves. And so in each problem, you've got to decide, is this a transverse wave that goes like this, or is this a longitudinal wave that goes sloshing like this? If it's a transverse wave, you use that formula. Sound wave, this formula. Longitudinal, this formula. Okay. Now, you should have an exam preparation sheet, and on the back of that exam preparation sheet is this old exam question. This exam question is a little bit more difficult than you would be expected to work on your exam. But it's a good practice problem. Indeed, when I put this on an exam some 30 years ago, it proved to be very, very hard, and many of the students didn't get it right. What we're told here is that this tube, it's a very long tube of 5 meters long, has water in the bottom of it, and the water's just there to form a hard barrier so that I have to have a node down there. The open end of that air column is going to have an antinode. And so if I want to know what's the fundamental frequency, I have to remember that I can't see a frequency. I can't draw a frequency, but I can draw a wave, okay? And I know that the wave is going to look like that. The longest wave that fits from the node to the antinode, the longest wavelength is the lowest frequency, the fundamental frequency, okay? And so it looks like if that half a football is 4.25 meters, well, then the wavelength is going to be 4 times that, or 17 meters. See if your neighbor sees that as obvious. Do a buddy check real quick. Why is it 4 times the length of that air column? Thank you for doing that. Okay. Again, it takes 2 footballs to make a wavelength. I only have half a football. That's 1/4 of a wavelength. 1/4 of a wavelength. Now, in this problem, when they were taking it as an exam question, I had to make an announcement to the class. Okay. Everyone was having so much trouble with it that I decided to make the math a little bit simpler. And so I told them, let's make it a cold day, a really cold day, so that the speed of sound is 340 meters per second. That's going to make the numbers work out so much easier so that we can work them in our head. So now, if we have a wavelength of 17 meters, if I take the speed of sound of 340 and divide it by 17, I get 20 hertz. And so that's going to be the fundamental frequency, 20 hertz. And what you would hear if you put a 20 hertz tuning fork above that would be a booming sound at 20 hertz. Okay? And probably not, because that's just a little bit outside of your range of hearing. But what if I put a tuning fork that was 40 hertz? Would it make a booming sound? No or heck no? Heck no. What about 60 hertz? Yes. And 80 hertz? No. 100 hertz? Yes. Okay, I get all the odd harmonics. Okay. Well, what if I take a tuning fork of 340 hertz? Is that going to resonate? Is that going to make a booming sound? Quick math. Turns out that 340 is 17 times the fundamental frequency of 20 hertz. Okay, so that's going to resonate. That's going to make a booming sound at 340 hertz. Now, what's that going to look like? How many footballs are going to be in there? Tell your neighbor. How many footballs are going to be in there?
Half footballs.
Okay. There are two ways of going about this. One way is to say, well, the ends are different. I started with half a football. That means that the 17th harmonic must have 17 times that many footballs. 17 half footballs is 8.5 footballs, is it not? It is, okay. So what I have is 8.5 footballs. Now the second way to do that is to figure out the wavelength for this tuning fork. Well, V is equal to lambda times the frequency. If this is 340 meters per second, and this is 340 hertz, what do I have to multiply 340 by to get 340? 1. So the wavelength of this tuning fork is 1 meter. That means I have footballs that are half a meter. Okay, let me show you. How big is a football? Well, a wavelength is 1 meter. It takes 2 footballs to make a wavelength. 1 football is a half meter. And so I ask, how many half meters can I fit in 4.25 meters? 8.5. 8.5. So either way you find that, it's valid. Okay, does that make sense? Questions on that? Yes, sir.
You just explain that one more time, just how the first way, I mean, going to 8 footballs. Like, the velocity, frequency, and wavelength makes sense, but how did you do it without using that equation?
Well, remember, because of that wave equation, if the frequency just got 17 times bigger, the wavelength has to get 17 times smaller. Okay? And that means I can fit 17 times as many footballs in the same space. Well, I started with half a football. If I can fit 17 times that, or 17 half footballs, that's going to be 8.5. Make sense? Okay. Now, what we find is in this problem, if we drain some of the water out of that column, the resonance goes away. We don't hear that booming sound that we heard. It goes away. But if we lower the water just the right amount, it comes back. Just the exact same sound we heard before. And the question is, how far do I have to lower the water? Well, the reason it goes away is that I only get the resonance when the wavelength fits the boundary conditions, where the wave is just the right size so that I can have a node at the bottom where it's solid and an antinode at the top where it's open. And if I lower it just a little bit, it doesn't fit anymore, unless I lower it enough to fit 1 more football. If I lower it by 1/2 meter, I can fit 1 more football, and then I'm going to meet the boundary conditions. I will again have a node here and an antinode there. Yes,
What would that do to the sound?
what happens to the sound? Because the footballs are the same size, I would hear exactly the same note. But now it would be the 19th harmonic of a new fundamental. Because I've changed the length of the air column, it's not a fundamental of 20 hertz anymore. It's a fundamental of 18 point something hertz. And now I've got the 19th harmonic because I've got 19 half footballs in there. Okay? Yes.
Could you explain the boundary condition?
Boundary condition is just a closed end has to be a node and an open end has to be an antinode. It's just what's going on at the boundary of my system, at the ends of my system.
How does that apply to the tutorial where we had the spring on with the loose end?
Oh, it doesn't. It's a different use of the language. In that case, there's only one boundary because we're not setting up a standing wave. Those were traveling waves. And so when we say boundary condition, it's just what happens at the place where it bounces back. That one boundary. But here I've got two boundaries, and that's how I get the standing wave. Okay?
You get the point size.
Oh, right here. Because that was 340 and that was 340, the wavelength was 1. It takes 2 footballs to make a wavelength. So a football was half a wave. Okay. Now, I've got one more clicker question, and it's an important one, a very important one. I have come to realize the hard truth that we do not have enough TAs next semester in Physics 106, and we're not going to get any more. There just aren't that many people that are still going to be taking classes next semester that have experience with Physics 106. I hope to change that by getting a lot of you that are sophomores and juniors into the 106 class so that going forward we'll have a talented group of teachers. But I have to make a decision and I need your help. We can either staff a help center all week long, but if we do that, we can't run in-person tutorials. Instead, we would just watch a video of Greg working through the tutorial, and that would help you do your tutorial homework. The other option is we keep the in-person tutorials, but then we don't have enough people to run a help center for more than a couple of hours a week. And the third option is, neener, I don't have to take Physics 106. So with your clicker,
Demonstration and trust.
okay, if you click, you're free to go, people.
Want to see the answer?
Oh, do you want to see the answer?
Yeah,
Oh, yeah.
yeah,
Yeah.
SeaWorld.
Show us, Greg. Show us.
Show us, Greg. Great, you just
So let it be written, so let it be done. Have a great weekend.